Hello, my dears. Here we will discuss the ohm meter and digital voltmeter design and operation. We will start by ohm meter. In ohm meter, we are going to study the series ohm meter. In terms of construction, the ohm meter will use PMMC, the permanent magnet moving coil. Here is the PMMC. And there must be an internal resistance in series with it. To measure the resistance, we always need battery. So battery is needed. And here between point A and point B, we connect the resistor to be measured. Just to make you clear about this point, if this is the ohm meter, and I want to measure this resistance, we are going to connect the terminal of the voltmeter to this point and this point. These 2 points are point A and B. So I mean this one and this one. So this is Rx, where here is Rx. So now, how the measurement is going to be? The measurement, as you know, PMMC will feel current, will move based on the current coming in. So the current is coming from this source. If you look at the circuit carefully, you are going to find that the current is proportional to the value of Rx. That means the value of Rx will decide on the current, which means the value of Rx will decide on the deflection of the PMMC. This is the idea of this kind of meter. We will see in the next slide the equation to evaluate that current. But before that, I would like to tell you that in the ohm meter, the case is not unlike the voltmeter or ammeter. In what sense? In the range, in the sense of range. So when you look at the range of the ohm meter, you will find that it starts at infinity, which means when I'm not connecting any resistance here, when there is no resistance connected here, the ohm meter will give me between A and B infinity. And as we are connecting resistor between the two terminals, when there is a resistance, that means there is a current flowing. If there is current flowing, means there will be a deflection in the PMMC. So remember, if there is no resistance here, there is no deflection. So it's supposed to indicate infinity. That's the idea. The meter current, or the ohm meter current, it's the current flowing to the PMMC, which will be affected by the value of Rx, as I mentioned earlier. If you look at this equation, the equation here is showing the current going to the PMMC, so that it's going to result in a deflection. It's affected by the battery voltage and Rx, which is the measured resistance, with R1 and Rm, the internal resistance, and the PMMC resistance. So now the scaling or the ranging of the meter is something very important. As I mentioned just now, we are going to keep in our mind that the range of the meter is supposed to start with infinity. It must indicate infinity when there is no resistance connected, because the circuit is going to look like this. So here is R1, this is Rm, and this is Rx. So right now, if there is no current flowing, if there is no resistance connected between these 2 points, that means no current flowing. The meter must indicate infinity. That's one thing. The other thing, the other point is when the resistance is connected, when there is a resistance connected between A and B here, it's supposed to give me some current flowing. There will be a movement. The point is not this. The point, what if this resistance value 0 means short? If the resistance is short, the meter is supposed to give me the indication of 0. So we have to make the design of the meter such that with short circuit, it gives me 0 value, or the value of resistance will be 0. And with open circuit, when this is open circuit, it's supposed to give me infinity, as you see here. This is the point. That's not the only thing. We have to keep in our mind also the half scale deflection. Half scale deflection means the pointer supposed to go to this position. I mean the half scale deflection. When there is rule for that. the meter supposed to go to half scale deflection when the resistance connected here, this resistance, equal to the internal resistance. So this is to be kept in our mind as well. So whenever the resistance measured equal to the internal resistance of the meter is supposed to give me half range. So now it's clear. Short circuit, the meter is supposed to give me 0. No, or open circuit or no resistance connected, the meter is supposed to give me infinity. And if the resistance measured equal to the internal resistance of the meter, the meter or the pointer is supposed to give me middle range reading. Let us check how the questions on the ammeter to be asked. Actually, it's simple because it's series circuit as you see here. So it's simple to deal with it. Let us see how the question is to be asked. The series ohmmeter of the figure below is made up of 1.5 battery. So the battery here is 1.5 volt. 100 microampere meter. I mean the PMMC here, the rating of the PMMC is 100 microampere. It means the full scale deflection is 100 microampere. We are not allowed to let more than 100 microampere to flow in the circuit. And the resistance R1, which makes R1 plus Rm is equal to 15 kilo ohm. He means the internal resistance equal to 15 kilo ohm. R1 is actually both. He make them here such that R1 is both R1, which we know it as R1, and Rm. Both of them equal to 15 kilo ohm. Determine the instrument indicating when Rx equal to 0. I mean, if this value equal to 0, what is the indication of the meter? How is it going to indicate? Look, before we read or look at the answer, we have to make it such that when 100 microampere flow in the meter is supposed to point at 0 ohm, because this is the full scale. We have to keep this in our mind. When the current flowing to the meter is 100 microampere, the meter is supposed to indicate me 0 ohm. Okay, let us calculate the current. So when we calculate the current, I is equal to EB over Rx plus R1 plus Rm, where Rx equal to 0. So it means it's equal to 1.5 volt over 15 kilo ohm equal to 100 microampere. Which means if you connect a short circuit here, the meter will indicate 0. The current will 0. Why it's indicating 0? Because the full current goes to the meter, which make it at full scale. So the pointer will move to its maximum value, where the maximum value will give me 0. Again, current flowing here is 100 micro. We agreed earlier from the question that 100 micro is going to make the pointer to its maximum deflection. Now its maximum deflection is indicating 0 ohm. So what he want from us here is to calculate Im equal to 100 microampere. Now how about 0.5 of full scale deflection? Remember, this is the middle range. So if the case is like this, that means we are going to allow 50 microampere to flow. Half or 50% of the middle, 50% of the PMMC current means 50 microampere. So we will assume 50 microampere is flowing. That means Im will not be 100 micro, will be 50 micro. So if it's 50 micro, we will check what is the reading. So now I know that Rx plus R1 plus Rm equal to EB over I. The total resistance equal to the voltage divided by the current. Current is 50 micro, the voltage 1.5, which means from there we can calculate these resistors. But these two are 15 kilo. The remaining will be the value of Rx. Let us see it in the next slide. So here, as a result of what I said just now, Rx equal to 15 kilo ohm. Remember, this is very good point actually, because at the middle range, we reach to the middle range when we allow 50 microampere to flow. we reach to the middle range. I reach to the middle range when the measured value equals to the internal resistance of the meter, which 15 kilo ohm, which very good point. Now, what will be the situation if we allow 25% of the current to flow, 0.25 of the full scale deflection? So 0.25 of the 100 means 100 over 4, however you calculate it. 0.25 multiplied into 100 equal to 25 micro. If a 25 microampere flow, what is the reading at that time? We are going to keep in our mind that this is A and B. Here is the battery. This is RM here. So now we have resistor here. We don't know what is the value, but it makes the current flowing here equal to 25 microampere. What is the indication here, or where the indication going to be? Indication will be somewhere else, somewhere here. So what is the value at that time? So we will check. Of course, it's equal. The voltage is fixed. 1.5 over 25 micro is equal to the total resistance, same as before. So Rx is equal to 1.5 divided by 25 micro minus R1, or internal resistance, equal to 45 kilo ohm. That means this resistance is 45 kilo ohm, which means the meter here is supposed to give me the indication of 45 kilo ohm. Remember, this one just now give me 15 kilo ohm. Let me proceed. How about 75%? 75% will give me, by calculation, same way, the current is 75 microampere. So we will calculate Rx to find that it's 5 kilo ohm, which means the meter will be here. So the point here is equal to 5 kilo ohm. So that's how I can figure out the scale of the meter. The point of, or the important element in the ohm meter is to decide on the scale. Ohm meter with zero adjustment. Let us consider one of the cases given in the previous example. The case is when the meter at the middle range. When the meter at the middle range, we find that the voltage or the current flowing, let's say 1.5 volt divided by 30 kilo ohm equal to 50 microampere. So 50 microampere will put the emitter at the middle range, where there we wrote 15 kilo ohm. So it's going to make the pointer at the middle range, where the middle range is 15 kilo ohm. That's what we discussed in the previous example. What will be the situation if the voltage here drop to 1.4? You will find this value is going to be less. If the value is less, that means the pointer will point at this position, which give me different reading for the same resistance value. For that, we need to have what is called ohm meter with zero adjustment. We have to get the zero adjustment. The zero adjustment will adjust the voltmeter, the ohm meter, when the battery drop. When the voltage of the battery drop, we can adjust the ohm meter to measure the correct value always. To understand the zero adjustment, actually it's going to be obtained by adding this resistor. As you see, it's variable resistor and it's going to have some current in it. Now, when the battery voltage drop, we will adjust this resistor such that the current flowing here is the required current to make the required deflection. That's the idea. So if the voltage drop, we will find that IB drop or decrease. If IB drop, what we will do, we are going to adjust this resistance value to increase the current going here to its original value. So in my previous example, I want the middle range. The middle range supposed to be 50 microampere. If the voltage here drop from 1.5 to something lower like 1.4, we will find this value is getting less. So if the value getting less, what we will do, we will adjust this resistor to bring this value back to 50 microampere. The next example will explain this point to us in a clear way. Before we discuss the example, let us look at the meter current. The meter current is to be calculated when the ohm meter has zero adjustment. Is to be calculated by this formula, where it's equal to EB over Rx plus R1 plus R2 parallel RM, R2 parallel RM, They are to be mixed together. Now, in general or usually, we will find that R2 parallel Rm much smaller than R1. These two resistors much smaller than this one. So we can neglect R2 parallel R1 sometimes in our calculation. So we will find that IB can be calculated as a EB over these two resistors only. Because as I said, these two values are smaller or much smaller than these two values. Also, the meter voltage can be calculated as, when we say the meter voltage, that means this voltage. We can calculate it as IB multiplied by IB. Here, this is IB, the current flowing from the battery, multiplied into R2 parallel Rm, means into this combination. Let me just erase to see the things clearer. So IB is flowing. If I get these two resistors in parallel, IB multiplied in both of them will give me a voltage between this point and this point, which is known as Vm. Im, the current Im, means the current flowing in the meter, yes, in the PMMC here, can be calculated as IB into the combination of parallel resistors, means the current here multiplied into these two resistors, which equal to Vm. Notice that this is Vm divided by Rm. That's how I can calculate the current going to this branch. If I want to get the current I2, we can calculate the same way. It's going to be Vm divided by R2. That's how we can calculate the currents in this kind of circuits. Let us consider this example. It's an ohm meter, which shown here in the figure has the voltage of the battery with a voltage of 1.5 volt. R1 equal to 15 kilo ohm. This is 15 kilo ohm. Rm equal to R adjustment equal to 50 ohm. We mean this one equal to 50 ohm, and this is 50 ohm. I full scale deflection equal to 50 microampere. That means the current which will flow here to make a full scale deflection supposed to be 50 microampere. Calculate Rx at 0.5 full scale deflection when the battery is 1.5 volt. So we need to calculate the value of Rx, this value, when the pointer is pointing at middle range here. Remember, 50 micro will give me full range. That means middle range supposed to be 25 micro. From there we will start our calculation. Let us check the answer in the next slide. So here is the answer. First of all, we will calculate Vm, which equal to Im Rm. Im into Rm equal to Vm, which to be calculated as a 25 into 50. Remember that 25 microampere is to be considered because we want it to be in the middle range. It's going to result to 1.25 millivolt. That means the voltage between this point and this point is 1.25 millivolt. Now I adjustment, the current going to the adjustment resistance is going to be equal to the voltage between these 2 points divided by this resistance. That's it. So it's as simple as this. Again, the voltage here divided by this resistance. So when we calculate the voltage, which equal to the same voltage as Vm divided by R adjustment, it's equal to 25 microampere. That means also here we have a 25 microampere. Now what is IB or I total? We call it IB or I total, which means this current. What is it equal to? It's the total currents. Here 25, here 25. That means here we are going to get 25 plus 25, which equal to 50 micro. So here we are having 50 micro. IB here is equal to 50 microampere. In this case, we can calculate both of Rx and R1 from the equation mentioned earlier, the approximation. If you remember just now, I said these two resistors in parallel are much smaller than the resistor R1. That's why we can neglect them. So here we will neglect them. If we neglect them, we are going to calculate these two resistors as E over IB. E is 1.5 over IB or I total, which equal to 30 kilo ohm. That means these two resistors equal to 1 kilo ohm. These two resistors equal to 30 kilo ohm. It's mentioned earlier that R1 equal to 15 K, this one in the question, 15 kilo ohm. That means this one will be 15 kilo ohm. That's how we can calculate it if there is R adjustment in the circuit of ohm meter. The other part of the question where he asked me to calculate the value of R adjustment if the voltage of the battery dropped to 1.3 volt. This battery is no more 1.5, it's 1.3. So if I keep everything as it was before, I will find at middle range, the current here will be less than 25 ohm, 25 microampere, which going to give me wrong reading. That's why he said we need to adjust this resistance to make the current here 25 microampere again for the same value. Let us see what the question wants. Here the question is saying we need to calculate R adjustment to maintain the current or to get me the value of full scale deflection now, not middle range, full scale deflection. Remember, full scale deflection is 50 micro. That means what is the value of Rx making the current here equal to 50 microampere? Because again, 50 microampere is going to be the full scale deflection. How to calculate it? We will calculate the total current. Total current here, it's equal to E over Rx plus R1. Remember that Rx is 0 now. Why it's 0? Because you want full scale deflection. He is asking for a full scale deflection, and the full scale deflection is supposed to give me 0 ohm reading. That's how I know that Rx equal to 0. The plus 15, that means these two resistors are 0 plus 15K. When we calculate, we find that this current is equal to 86.67 microampere. Now I will calculate I adjustment. I adjustment is supposed to be equal to I total minus the full scale current, because I want the current here to remain 50, to be 50. I want the current here to be 50. Then what is the current supposed to go to this side? It's going to be the total current minus the 50, which equal to 36.67. Now, if you notice, we have the current going here, we have this current, and also we have Vm. Vm can be calculated because I have here 50 and we have this Rm. We have the current here flowing is 50 and here the resistance is 50 micro and here 50 ohm. 50 micro and 50 ohm. So from the 50 micro and the 50 ohm, we will be able to calculate Vm. Now, if I have Vm, Vm is again the voltage of this resistance. Earlier we calculate the current here, which found to be 36. And now we calculate the voltage, which will be found from this here to be 2.5 millivolt. The voltage over the current will give me the resistance of the adjustment. I mean, the resistance which is supposed to be. So Vm over I adjustment, we calculated to find the value of R adjustment equal to 68.18 ohm. Remember earlier, before the battery lost part of its voltage, the resistance here was 50 ohm. Before that problem, before the problem of the battery, we found, or we have the resistors. This one was 50 and this is 50. When the battery lost 2 or 0.2 volt, it becomes 1.3 rather than 1.5. This resistor, instead of 50, it becomes 68.18. Why? To allow the current going here is the right current.